Hello all, welcome back to Climate Dynamics. In today's lecture, we're going to continue to explore the past and future of the Earth's climate system. Today's lecture focuses specifically on changes to the Earth's climate that have been experienced since industrialization, and looking forward into the future, what influence human activities will continue to have on the climate system. The reading for today's lecture is the IPCC Fifth Assessment Report, Working Group 1, which can be found in the link here. In this section, we'll address 4 questions. First, what is the Intergovernmental Panel on Climate Change? Second, are human activities responsible for warming the Earth? Third, what are the major drivers of anthropogenic climate change? And fourth, how do we experience climate change? Before proceeding, we want to discuss how exactly we study climate change. Most of our knowledge on climate change is collected by an organization known as the Intergovernmental Panel on Climate Change. This organization was established in 1988 by 2 United Nations organizations, the World Meteorological Organization, or the WMO, and the United Nations Environment Program, UNEP. The mission of the IPCC is to provide comprehensive scientific assessments of current scientific, technical, and socioeconomic information worldwide about the risk of climate change caused by human activity, its potential environmental and socioeconomic consequences, and possible options for adapting to these consequences or mitigating the effects. What is worth noting is that the IPCC itself is not a scientific organization. That is, it does not conduct science itself, but instead is a body that collects scientific information from researchers worldwide and places them into a single organizational unit that can then be reviewed by policymakers and stakeholders in order to understand the future of climate change. The administrative structure of the IPCC is shown here. At the top, we see the IPCC plenary, which contains representatives from governments all over the world. The IPCC Bureau contains representatives from both the IPCC executive as well as chairs and vice chairs of the individual working groups. Finally, the executive committee consists of the chairs and vice chairs of the IPCC and makes executive decisions on behalf of the IPCC. Key to the IPCC is its segmentation into 3 main working groups. The first working group addresses the physical science basis, that is, key scientific questions related to how exactly the climate system operates, and how, through our activities, we are influencing that operation. The second working group deals with impacts, adaptation, and vulnerability, that is, to understand how changes in the climate system can then impact our world and how we can adapt to those changes. The third working group deals with mitigation of climate change, that is, how to avoid future climate change. And finally, we also have the Task Force on National Greenhouse Gas Inventories, as well as other task forces that are assigned by the IPCC. The IPCC also includes representation from scientific authors, contributors, and reviewers worldwide, whose research is then accumulated in the production of semi-periodic assessment reports. These assessment reports then contain the sum total of human knowledge on the study of climate change to date. This schematic represents some of the topics that are explored in the semi-periodic IPCC assessment reports. On the top, we see climate change, extreme events, sea level rise, temperature change, and precipitation change. These are primarily changes that occur within the Earth system. However, these changes are interconnected with climate process drivers, that is, greenhouse gases and aerosols, including concentrations and emissions, as well as impacts and vulnerability, that is, how climate change impacts ecosystems, food security, water resources, settlements and society, and human health. On the human systems side, the IPCC also studies socioeconomic development in order to understand population changes, equity, including climate justice, production and consumption patterns, trade, governance, health, sociocultural preferences, technology, and literacy. In addition, these socioeconomic drivers are connected intimately with mitigation and adaptation strategies that can then be used to address climate change. The most recent assessment report that has been published by the IPCC is the Fifth Assessment Report. This was published from September 2013 through October 2014 in chunks. Again, the 3 main working groups that contributed to the assessment report were the Physical Science Basis, Working Group 1, Impacts, Adaptation, and Vulnerability from Working Group 2, and Mitigation of Climate Change from Working Group 3. Finally, there was an AR5 synthesis report that was finalized on the 31st of October 2014. The next assessment report, the sixth assessment report, is expected to be published in late 2020 through 2021. What the IPCC has shown since its first assessment report is that there is growing evidence supporting the conclusion that humans have had a discernible effect on the climate system. We can look at the statements that have been made in past assessment reports to see the growing confidence in this conclusion. In the second assessment report, the consensus statement was that the balance of evidence suggests a discernible human influence on global climate. In the third assessment report, the statement that was adopted was, there is new and stronger evidence that most of the observed warming over the last 50 years is attributable to human activities. In the fourth assessment report, the conclusion was that most of the observed increase in globally average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. The term very likely here has a very specific scientific meaning that is derived from meta-analysis. And in the fifth assessment report, the most recent report that has been published, the statement is crystal clear. The science now shows with 95% certainty that human activity is the dominant cause of observed warming since the mid-20th century. The report confirms that warming in the climate system is unequivocal, with many of the observed changes unprecedented over decades to millennia. Warming of the atmosphere and the ocean, diminishing snow and ice, rising sea levels, and increasing concentrations of greenhouse gases. Each of the last 3 decades has been successively warmer at the Earth's surface than any preceding decade since 1850. Since this statement was made in 2013, the evidence has only continued to grow, and I entirely expect that with the sixth assessment report, we will see an even clearer statement of the influence of human activity on the climate system. How have we derived these conclusions? We know that there are both natural and anthropogenic contributors that can influence the climate system. The 3 major natural mechanisms that influence climate include changes in solar forcing, changes in the amount of volcanic dust in the atmosphere, and internal variability of the coupled atmosphere-ocean system. The relative contributions of each of these components can be studied in order to assess its total contribution to the warming that has been experienced to date. There are also 3 primary anthropogenic mechanisms that can influence the climate system, including changes in atmospheric concentrations of greenhouse gases, specifically through industrial activities, changes in aerosol particles from burning fossil fuels and biomass, and changes in the reflectivity or the albedo of the Earth's surface. Changes in reflectivity are primarily because of human influence on land use land cover change. That is, it includes things like clear cutting of forests and planting of cropland, which can have widespread effects on the reflectivity of given regions. By studying each of these individual contributors, we can then tabulate the individual radiative forcing due to each of these contributions. This chart from the 5th assessment report shows recent contributions to radiative forcing at the surface relative to the pre-industrial, here taken to be 1750 AD. Radiative forcing in this case refers to changes in surface received radiation from above. Changes to concentrations of greenhouse gases in the atmosphere, for instance, can impact the amount of terrestrial radiation that's reflected back to the surface, and hence contribute to a change in the surface received radiative flux. At the top of this table, we actually see those well-mixed greenhouse gases being primary contributors towards increases in radiative forcing. At the very top of the table, we see carbon dioxide, which is responsible for a contribution of about 1.68 watts per meter squared. Next, we have methane, which is also a dominant contributor towards overall warming. Then we see ozone, chlorofluorocarbons, and the hydrochlorofluorocarbons. CFCs, although they appear in relatively low concentrations within the atmosphere, are nonetheless very powerful greenhouse gases. Finally, the 4th row of this table shows nitrous oxide, which is again a powerful greenhouse gas associated with anthropogenic activity. The next 3 rows show short-lived gases that are also associated with modifying radiative balance. These include carbon monoxide, non-methane volatile organic compounds, and other NOx species. The overall contributions from these gases is much smaller than that from the well-mixed greenhouse gases, but nonetheless they do have a contribution to overall radiative balance. The level of confidence in the effects of these gases is also somewhat less than that of the well-mixed greenhouse gases. The next two rows then show aerosol effects. In particular, aerosols generally cool the climate system because they act as little mirrors for incoming solar radiation. That is, aerosols in the atmosphere have a tendency to scatter and reflect incoming solar radiation, which then produces a cooling effect on the planet. The only exception to this is black carbon, which is a form of aerosol that is produced generally from biomass burning, but is a net absorber of incoming solar radiation. Thus, black carbon in the atmosphere has a tendency to warm the climate system. The row below this shows cloud adjustments due to aerosols. That is, with greater aerosol concentrations in the atmosphere, we also have a greater tendency to produce clouds. That is, these aerosols act as cloud condensation nuclei for the formation of cloud droplets. And so with more aerosols in the atmosphere, we can produce more cloud, and cloud, it turns out, has a high albedo associated with it, and thus will reflect incoming solar radiation. These two rows, in particular, have very large error bounds associated with them. That is, we still are trying to narrow down the explicit contribution from aerosols to the total radiative forcing. In particular, the contributions from aerosols in this first row have the potential to be positive, depending on relative concentrations of black carbon versus the other aerosol species, as well as its power in absorbing incoming solar radiation. The next row shows albedo change due to land use. That is, human actions that have resulted in the change of the actual land cover of the planet have resulted in changes to its albedo as well. Clear cutting of forests and replacing those forests with cropland affect the albedo and hence the reflectivity of the surface to incoming solar radiation. The net change because of human activity has been to increase the albedo overall, and thus this albedo change has resulted in a net cooling effect on the planet. Below that, we now have our natural contributor to overall radiative balance, which is changes in solar irradiance. The change in solar irradiance turns out to be a very small warming effect on the overall radiative balance. In summary, the weight of scientific evidence indicates that it is primarily anthropogenic activities that have modified radiative forcing at the surface, and hence are responsible for near-surface warming. The primary contributor to that near-surface warming is through well-mixed greenhouse gases, in particular carbon dioxide, but also gases including methane, halocarbons, and nitrous oxide. We have also modified the radiative balance of the surface through activities such as aerosol emissions and through land use change. Generally, aerosol emissions and land use change produce slight cooling effects on the surface, although the error bars associated with these contributions are relatively larger than those of the well-mixed greenhouse gases. Natural forcings tend to be fairly small by comparison. Okay, recall that we talked earlier in this class about the greenhouse effect. The greenhouse effect refers to the trapping of terrestrial radiation by greenhouse gases in the atmosphere. So, in the previous slide, this reference to well-mixed greenhouse gases specifically refers to those gases that are involved with the greenhouse effect. That is, those gases absorb outgoing infrared radiation from the surface and consequently warm the atmosphere, leading to more emission back down to the surface. Consequently, the radiation is effectively trapped in the near-surface region. Where do these greenhouse gases come from? Well, we can go through them and categorize the sources associated with each of the gases. Water vapor is of course the strongest greenhouse gas, but you notice in the previous slides it did not show up in the actual graph. That's because water vapor itself is actually regulated by the climate system. That is, human emissions of water vapor will simply lead to air becoming more saturated and consequently that air precipitating. On the other hand, carbon dioxide is a well-mixed greenhouse gas, one that is relatively inert and one that is not easily washed out of the atmosphere. Carbon dioxide emissions from anthropogenic sources come from burning fossil fuels, including coal, natural gas, and oil, as well as solid waste, trees and wood products, and also as the result of certain chemical reactions, such as the manufacturing of cement. Carbon dioxide is removed from the atmosphere or sequestered when it is absorbed by plants as part of the biological carbon cycle. That is, through photosynthesis, carbon is naturally absorbed by vegetation and used in order to build up that vegetation. When vegetation then dies, it can be sequestered in the earth. or it can be released back to the atmosphere. It depends entirely on the particular vegetation type. In terms of U.S. greenhouse gas emissions in 2016, carbon dioxide accounted for the vast majority, that is, 81% of that total greenhouse gas inventory. Methane is the next most emitted gas, accounting for 10% of total U.S. greenhouse gas emissions. However, per molecule, methane produces approximately 11 times more warming than carbon dioxide, and consequently, it is a very powerful greenhouse gas. Methane is emitted during the production and transport of coal, natural gas, and oil. Methane also is a major byproduct of agriculture, particularly livestock such as beef and lamb. Methane also comes from the decay of organic waste in municipal solid waste landfills. Methane, however, does have a much shorter lifetime in the atmosphere. Whereas the lifetime of carbon dioxide can be in excess of 100 years, methane typically exits the atmosphere within approximately 11 years. The next most emitted gas is nitrous oxide, or N2O, accounting for approximately 6% of U.S. greenhouse gas emissions in 2016. Nitrous oxide is naturally emitted during agricultural and industrial activities, as well as during combustion of fossil fuels and solid waste. Nitrous oxide is a natural byproduct, for instance, of transportation infrastructure. Next comes fluorinated gases, responsible for about 3% of greenhouse gas emissions. These include hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and nitrogen trifluoride. This also covers chlorofluorocarbons, which you may recall are associated with refrigeration. These are synthetic gases, that is, they do not appear naturally. However, they are very powerful greenhouse gases and can persist in the atmosphere for a very long time. They are naturally emitted from a variety of industrial processes, particularly associated with refrigeration. In terms of total contribution to heating imbalance, carbon dioxide is associated with the largest contribution. However, the other greenhouse gases are not negligible. As you can see here, by 2018, carbon dioxide has contributed approximately 2 watts per square meter to total radiative forcing at the surface. Methane is associated with approximately half a watt per square meter. The other gases, including nitrous oxide, chlorofluorocarbons, and minor gases, are again associated with approximately half a watt per square meter. Thus, in total, by 2018, our total greenhouse gas emissions have been associated with approximately a 3 watt per meter imbalance from pre-industrial. Let's look at carbon dioxide for a moment. We've discussed carbon dioxide concentration previously in the atmosphere when we talked about the chemistry of the atmosphere. Carbon dioxide concentrations have continued to increase along with continued industrial activities. The Keeling curve, named after Charles David Keeling, who started the carbon dioxide monitoring program at Mauna Loa Observatory in 1958, basically measures the change in carbon dioxide contributions over time. What we see from the Keeling curve is a consistent increase in the total amount of carbon dioxide, reaching in excess of 400 parts per million in recent times. Prior to industrialization, carbon dioxide concentration sat at about 280 parts per million. We also see a seasonal behavior associated with carbon dioxide concentration. This is because during the northern hemisphere spring and summer, vegetation uptake of carbon dioxide leads to a reduction in total atmospheric carbon dioxide concentration. However, during the fall, that carbon dioxide is again re-emitted back to the atmosphere. And so carbon dioxide emissions increase during the northern hemisphere fall and winter periods. The same does not hold in the southern hemisphere, because the southern hemisphere has far less land area, and hence cannot uptake as much carbon dioxide as the northern hemisphere. In our discussion during the paleoclimate lecture, we saw that carbon dioxide concentrations were closely associated with temperatures. If we go back in time, up to 800,000 years ago, we see that total carbon dioxide concentration in the atmosphere was in a fairly narrow range, between approximately 180 parts per million and 280 parts per million. The highest previous concentration of carbon dioxide was about 300 parts per million, occurring over 300,000 years ago. Present-day values of carbon dioxide are much larger than anything that has been seen in the past 800,000 years. This can only be attributed to anthropogenic activity. There's an excellent video that explains the history of carbon dioxide in the atmosphere, produced by NOAA and other global collaborators. The link to this video can be found here. Science says that atmospheric carbon dioxide concentrations and temperatures are self-reinforcing. In our lecture last time, we talked about the feedbacks that occur between oceanic temperatures and carbon dioxide concentration. In the paleoclimate record, we saw that carbon dioxide concentrations slightly lagged behind temperatures because oceans naturally released carbon dioxide during warm cycles into the atmosphere. This reinforced the warming and led to even warmer oceans. The feedback mechanism that we explained last time is shown here. Whereas in our paleoclimate discussion, we talked about external forcing driving warmer ocean temperatures, perhaps associated with the recession in sea ice extent. This, in turn, drove lower oceanic carbon dioxide solubility, that is, releasing carbon dioxide into the atmosphere, which then enhanced greenhouse warming, which then enhanced oceanic temperatures. Consequently, in the paleoclimate record, we would expect to see that carbon dioxide lags behind the oceanic warming. On the other hand, at present, we are responsible for driving the increased carbon dioxide emissions by burning fossil fuels. By burning fossil fuels, then, and emitting this carbon dioxide directly into the atmosphere, we expect that the carbon dioxide we emit will then trigger warming. That is, carbon dioxide emissions will lead warmer oceanic temperatures. This also produces a natural feedback, since the carbon dioxide that is kept within the oceans will also be released as oceanic temperatures warm. To learn more about how carbon dioxide moves throughout the atmosphere, I'll refer you to this video by NASA, which shows a year in the life of carbon dioxide and the atmospheric dynamics associated with carbon dioxide's movement through the Earth system. Satellite and in situ observations of near-surface temperatures have confirmed that warming is unambiguous. That is, for over the past 100 years, we have seen unprecedented warming of the near surface of approximately 1 degree Celsius or 1.8 degrees Fahrenheit over the 139-year surface temperature record. Many of the observed quantities that we would expect to increase if the surface was warming are increasing. Temperatures over land are increasing. Specific humidity is increasing, again a consequence of the Clausius-Clapeyron relation and the fact that warmer air can hold more water vapor, and air temperature near the surface in the troposphere is increasing. We also see increases in sea level associated with thermal expansion of water and increased melt of land ice. We discussed this briefly in the ocean section of this class. We're seeing increases in sea surface temperature as much of the warming is being constrained to the near surface layer. We're seeing increases in ocean heat content, primarily again in the near surface, but we are still seeing increases at depth as well. And we're seeing increases in temperatures over the ocean. The oceanic climate change indicators that should be increasing in response to higher greenhouse gas concentrations are increasing. Quantities that should be decreasing in light of warmer temperatures are decreasing. Northern Hemisphere March to April snow cover is decreasing. Glacier mass balance is negative, indicating the loss of glacier ice, and particularly acceleration of that mass loss. And sea ice extent is continuing to decline. That is, sea ice is no longer proceeding as far south in the Northern Hemisphere as it had historically. Here's a plot showing oceanic heat content. In particular, since the 1960s, we've seen a continuous increase in the total amount of heat stored within the oceans. This is particularly important because, as discussed in earlier lectures, the ocean is a massive reservoir for energy. And it is, in some sense, mitigating some of the warming that we are experiencing in the near surface because it can act as a reservoir for extra energy. We're seeing much of the oceanic heat content increasing throughout the near surface of the ocean, but we're also seeing ocean heat increase at depth. By comparison, the total change in land plus ice plus atmosphere heat content is only about 3 times 10 to the 22 joules, which is only a small fraction of the total amount of energy shown on this plot. So that is what we've been experiencing to date. What about in the future? How do we understand how climate change will be affecting us over the next 100 years? And how can we plan accordingly? In order to do so, we again fall back on the Intergovernmental Panel on Climate Change. Through this process, we have laid out a series of steps that allow us to assess future change in a scientifically valid and rigorous manner. To do so, we develop a set of socioeconomic scenarios. That is, we consult with social scientists in order to understand how population growth and industrialization will proceed into the future under a variety of possible policy and scientific scenarios. These scenarios then give rise to emission scenarios. That is, they allow us to project how much total greenhouse gases will be emitted into the atmosphere in order to sustain that level of growth. These emissions can then be used to develop total radiative forcing of the near surface, and consequently these can be fed into climate models in order to understand how the global Earth system will respond to this level of radiative forcing. Finally, these climate model results can be fed into impact, adaptation, and vulnerability assessments so that we can plan for an uncertain future in light of climate change. These future changes are typically represented using representative concentration pathways, or RCPs. These were developed for the fifth assessment report in order to provide realistic projections of future greenhouse gas inventories in the atmosphere. Although many such scenarios have been developed, we generally focus on 4 such scenarios. The first, RCP 8.5, refers to 8.5 watts per meter squared of forcing by end of century. It is a business as usual scenario where we assume that there is very little policy action and much of future energy need is met by fossil fuel emissions. On the other end of the scale, we have RCP 2.6, shown in the green curve here. This assumes very aggressive policy action in order to reduce fossil fuel emissions, as well as the development of technology that allows us to actually extract greenhouse gases from the atmosphere. In between these two scenarios are RCP 4.5 and RCP 6.0 that are middle-of-the-road scenarios that combine somewhat aggressive policy actions and corresponding technological improvements. In the forthcoming 6th assessment report by the IPCC, the focus is on shared socioeconomic pathways, which combine both greenhouse gas emissions with land use, land cover change. With these future change scenarios in hand, we can then run global climate modeling systems from around the world. These modeling systems are first assessed on history in order to ensure that they can reproduce the historical record of temperature change. Once they have been validated over this historical period, they are then run forward. Between 2005 and 2100, 39 models ran RCP 8.5, 25 ran RCP 6.0, 42 ran RCP 4.5, and 32 ran RCP 2.6. Several models then ran further into the future through 2300. What we see from these projections is that total global surface temperature change is anticipated to be between approximately 3 degrees and 5.5 degrees Celsius by 2100, depending on the particular climate model used. There is some uncertainty, of course, because of natural variability in the climate system. Under RCP 2.6, the range is much narrower, with an anticipated change on the order of 0.5 to 1.5 degrees Celsius. If these scenarios come to pass, we can anticipate many potentially disastrous changes. We're going to focus particularly on RCP 8.5 because, to date, we have seen very little deviation from relying primarily on fossil fuels in order to fuel our growth. Under RCP 8.5, we anticipate a global average rise of 0.2 degrees Celsius over the next 2 decades. This is coupled with a global average rise between 1.8 degrees Celsius and 4 degrees Celsius by end of century, depending on the particular emission scenario. Temperatures over land are expected to increase faster than temperatures over the ocean, and increase is expected to be larger at higher altitudes. This is associated with a phenomenon known as elevation-dependent warming. As mountain snowpack melts, the albedo of these higher elevation regions changes and is reduced, leading to more absorption of total radiative energy and consequently enhanced warming. We also anticipate there to be much more warming in polar regions because of the loss of sea ice. Particularly, the Arctic is anticipated to have approximately 3 times as much warming as the average location over the Earth. We also anticipate increases in precipitation due to increased evaporation and more water vapor in the air. Again, this is purely associated with the Clausius-Clapeyron relationship, and thus is associated with approximately a 7% increase in water vapor per degree Celsius. We also anticipate a speed up in the water cycle, that is, more rapid transition between evaporation and precipitation. We anticipate expansion of the Hadley cells that may lead to intensified storm track and perhaps desertification in regions next to the subsidence branch of the Hadley circulation. We also anticipate a global average precipitation increase between 3 and 5%. However, this is not a globally uniform increase. Actual change is highly dependent on the particular region. Generally, dry areas will become drier, whereas wet areas will become wetter. In the cryosphere, we anticipate accelerated melting of all aspects of the cryosphere will occur, including loss of snowpack, sea ice, and glaciers. We anticipate that sea level will rise via a combination of thermal expansion of the ocean and melt of land ice. We had discussed thermal expansion of the ocean in the oceanic part of this class. During the 20th century, sea level rose about 10 to 20 centimeters, or 4 to 8 inches. Again, this is not geographically homogeneous. Some areas of the world experience much more sea level rise than others, which is closely connected with the amount of local upwelling, which controls the temperature of the local oceanic column. Thermal expansion and ice melt each contributed about 50% to the rise. By 2100, rise is expected to be between 20 and 50 centimeters, or 8 to 20 inches above 2000 levels. Over this period, thermal expansion is anticipated to contribute the majority, or about 75% of the total rise. Ocean acidification is a natural consequence of high carbon dioxide levels in the atmosphere. Carbon dioxide will naturally equilibrate between atmosphere and ocean. Namely, as the ocean uptakes carbon dioxide, it will be converted to carbonic acid in the oceans. This is thought to have reduced the ocean pH by 0.1 since pre-industrial times. Further acidification of 0.14 to 0.35 pH is expected by the year 2100. We also anticipate changes to extreme weather. For instance, tropical cyclones, extratropical cyclones, and atmospheric rivers will all be impacted and will likely be associated with much heavier precipitation. Warmer oceans will cause the intensification of such storms. However, the frequency of these storms may also decrease. Okay, thank you very much for joining us to date. We've talked about now the various aspects of the climate system, as well as applied the concepts in this class to both the historical record of the Earth's temperature, as well as looking at the temperatures since industrialization into the future. Our final class next time will wrap up the concepts to date and provide a summary of what we've learned. Thank you.